Welcome to this highlights reel and summary of a course of presentations on Drillstring and drilling dynamics. My name is Ben Jeffryes. I'm now retired, but before then I was a scientific advisor with Schlumberger. The presentation series has 13 parts, and having loaded them to YouTube, I realized that there was nothing to show people a summary of what was in each part. So here is the summary and highlights. There are 10 lectures, 3 of which are split into 2, so 13 parts in all. The first one is an introduction and discussion of axial dynamics. After some description and photos of the equipment involved, I explain the simplified models being used, with everything reduced to one dimension, and the 2 time period limits: early times, when the bit and surface are isolated from one another, and late times, when for axial and fluid modes, the system can be modelled using a few lumped parameters. The late-time axial drilling dynamics looks like a one-pole low-pass filtered version of the surface motion. In the picture you see modelled the motion of the top and bottom of the drill string. I also introduce the dynamics of the fluid and the rotational motion. The next 2 presentations are on rotational dynamics. In the first part, 2a, I show what rotational motion looks like in both the time and frequency domain. The picture shows a spectrum of rotation velocity measured near the bit, with many low-frequency resonances, and also a few very prominent high-frequency resonances. I then show how the bit, as well as generating rotational vibrations, also amplifies them, even when the energy needed to remove rock does not vary with rotation speed. You can see in the image that although the reflected rotational wave has a lower overall size on the left, variations on the right have been amplified. In the second half, I start with a discussion of the viscous attenuation of drill string waves by the drilling fluid, and how interaction with the borehole wall can both attenuate or amplify at different frequencies, before showing examples of what stick slip at low frequencies looks like. The image shows how theory can account for the drill string going from continuous stick slip oscillations on startup at one depth to stable motion when deeper. Back on the theoretical side, I show how certain oscillations can be prevented, those that are generated when starting the drill string rotating, by using an appropriately timed ramp. The image shows a theoretical startup in a deviated well, where, using the black line, a double ramp, for the surface rotation speed, shown in the top left, it results in the bit rotation speed, shown in the top right, with virtually no startup oscillation. The third presentation looks at the implications on drill string dynamics of the periodic structure of the drill pipe, the alternating thin pipe and thick joints. First, the theory, showing how some frequencies propagate in the pass bands and others do not in the stop bands, and how energy generated at stop band frequencies on one side of the drill pipe stays there. The graph shows how there can be complete reflection in the stop bands from drill pipe. It is in these frequency bands that high-frequency torsional oscillations occur during rotary drilling. The illustration shows how one frequency of oscillation can spontaneously disappear to be replaced by another. I also look at how high-amplitude axial vibrations can occur, and how realistic near-periodic drill strings differ from their perfectly periodic equivalents, and how the interaction between tool joints and the drilling fluid generates small extra stop bands for axial waves. In the fourth presentation, I move on to the dynamics of the fluid system. After looking again at how small flow variations, or pressure variations near the bit, are low-pass filtered by the system, I move on to large flow variations, such as starting or stopping the pumps. To a good approximation, when the pumps are turned off, the flow through the bit declines linearly. On startup, however, the bit flow rate will take a much longer time to stabilize than the time the flow took to stop. The graph shows how this process can be sped up quite safely by bringing the pumps up to a higher flow rate and then down to the flow rate chosen for drilling. When there is a positive displacement motor, also known as a mud motor, in the drill string, the dynamics are more complicated. I show how short-term pressure changes across the motor are not fully seen above the motor due to their effect on the flow rate. The image shows how a torque spike results in fluid initially being held back and then released when the torque is reduced again. After looking at how motors can amplify axial oscillations and how to model reflections from the bit and motor together, I move on to high-frequency torsional oscillations below motors and show how they can be affected by factors such as the type of motor and the flow rate, including formulae such as that shown. The sixth presentation, the final presentation looking at the dynamics of the whole drilling process, is largely devoted to auto drillers, but there is also a section on how top drive controllers can help control rotational oscillations. We start with auto drillers which aim to control the weight on bit, first with the ideal case and moving on to when the weight measurement is filtered. Ideal weight auto drillers are unconditionally stable, but when filters are added, an unstable parameter range appears, as shown in the graph. The second half of the presentation moves on to using surface pressure as the control variable, applicable when drilling with a motor. In this case, even without measurement filters, the system can be unstable, as shown here. With filters, the parameter range for instability is more complicated, shown in this graph. However, using mixed control, auto drillers using pressure control can be stabilized. I will also talk about the connection between auto drillers and stick slip, and how top drive controllers can help with stick slip reduction. The seventh presentation is devoted to the acoustics of the fluid channel, directly relevant to fluid path telemetry between downhole and surface. After showing in more detail how the one-dimensional equations are derived, I look at the attenuation of fluid waves, in particular the transition to the quasi-static limit, shown here for the case of laminar flow. Then I look at how fluid waves are reflected from pressure drops, including the bit, and from mud motors. Finally, the transmission of pressure variations inside the pipe to the annulus is analysed, which can be considerable for a stiff annulus, such as encased hole or a drilling riser. The remaining three presentations are on bending and lateral motion. Presentation 8 on how the quasi-static lateral deflection in one section of a periodically constrained tubular propagates between sections, very relevant for steering. For pipe or collars lying on the side of the hole, where the constraints are the joints or stabilizers, perhaps surprisingly, the propagation is greater in the vertical direction, where for small forces the joints are fixed to the low side of the hole, compared to the lateral direction, where the pipe can roll. The diagram shows how a unit deflection in one span propagates for different parameters. The ninth presentation is also statics, but in this case for pipe under compression, without joints. The first half is an analysis of what happens to pipe under compression in a horizontal hole, in the horizontal and vertical directions. As is well known, in the horizontal direction, there is a threshold value of compression that must be reached before sinusoidal buckling results. But after this, so long as the compression is not excessive, only a small amount of bending results. I show how the system re-stabilizes so long as the compression is within about 35% of the threshold. I also analyze the stability of deflections in the vertical direction, where in contrast, infinitesimal deflections are stable, but as the compression increases, smaller and smaller finite deflections become unstable. In the second half, I look at vertical buckling and show that for buckling purposes, a hole only needs less than a degree of inclination to be considered deviated, and provide formulae for use in these situations. I go on to study physically realistic configurations for helically backward cylinders in horizontal holes. The diagram shows the variation in helix pitch and the normal force in various physical and one non-physical situation. Finally, in the 10th presentation, I look at the lateral dynamics of tubulars, both collars and pipe, in horizontal holes. Crucially, there is always a rolling resonance, and without compression, vibrations at less than the rolling resonant frequency will not propagate. As compression increases, the cut-on frequency decreases, until at the critical compression it reaches zero frequency, and static sinusoidal buckling results. The graph shows wave number versus root frequency for compressed pipe, with some propagation just below the rolling resonance, but a stop band appearing just above it. That's all the talk summarised. I hope that has encouraged you to find the presentations of most interest to you, or to move on to part 1, the introduction.